There is a number that lives inside every single GPS satellite currently orbiting Earth. It is not a coordinate. It is not a frequency. Not because of software bugs. It is not a signal strength. It is a correction factor, a small mathematical adjustment that engineers load into the system to account for the fact that the satellites up there are experiencing time differently than the receivers down here. Without that number, your GPS would be wrong by 10 kilometers every single day. Not because of signal interference, because of physics, because time itself runs at a different rate depending on where you are in a gravitational field and how fast you are moving through space. Einstein predicted this in 1915. We ignored the implications for decades. And then we launched GPS, and the universe immediately proved him right. That was the moment humanity quietly, without fanfare, without a single press conference, became a species that manages relativistic time corrections as a matter of routine engineering. We just never told anyone. Here is why that matters right now. Because the same corrections that keep your navigation accurate on Earth are being applied in far more complex forms to every deep space mission NASA currently has operating. Voyager, New Horizons, the Deep Space Network, the Europa Clipper, all of them are wrestling with relativity every single day. And the solutions engineers are building for those missions are not just keeping spacecraft on course. They are, quietly and without announcement, writing the technical manual for the first human colony on Jupiter's moons. Let's get into it. Most people have no idea that GPS is a relativistic technology. Ask someone how GPS works, and they will tell you about satellites and signals and triangulation. All correct. But they will almost certainly leave out the part where the entire system depends on a precise understanding of Einstein's theories of relativity to function at all. Here is what actually happens. GPS satellites orbit at roughly 20,200 kilometers above Earth's surface. At that altitude, they are significantly farther from Earth's gravitational field than we are on the ground. General relativity tells us that clocks in weaker gravitational fields tick faster. The satellite clocks, experiencing less gravity than ground-based clocks, gain approximately 45 microseconds per day relative to clocks on Earth. At the same time, the satellites are moving at roughly 14,000 kilometers per hour. Special relativity tells us that moving clocks tick slower than stationary ones. This velocity effect causes the satellite clocks to lose approximately 7 microseconds per day. Net result, the satellites gain about 38 microseconds per day relative to ground clocks. 38 microseconds sounds trivial. It is not. GPS works by measuring the time it takes for a signal to travel from satellite to receiver. The system needs timing accurate to within about 20 to 30 nanoseconds to give you a location accurate to within a few meters. 38 microseconds of daily drift is roughly 1,200 times larger than the acceptable error margin. Left uncorrected, the system would become useless within hours. So engineers correct for it. Every GPS satellite carries this relativistic offset baked into its clock rate before launch. The atomic clocks on board are deliberately set to run slightly slow on the ground so that once they reach orbit and experience the relativistic speed-up, they tick at the right rate. This is not optional. This is not a refinement. This is the foundation the entire system is built on. And here is the critical point. The relativistic effects on GPS satellites are relatively modest. We are talking about a system sitting in low Earth orbit in a gentle gravitational field moving at moderate speeds. The corrections are manageable, elegant even. Now take that same problem and scale it to the outer solar system, to Jupiter, to missions traveling at tens of kilometers per second through one of the most powerful gravitational fields in the solar system. The corrections do not scale up neatly. They become a different category of problem entirely. In 1977, NASA launched two spacecraft that would become the longest-running relativistic time correction experiments in human history. Not by design, by necessity. Voyager 1 and Voyager 2 were built to visit the outer planets and then keep going. Nobody at the time fully appreciated what managing their communications would eventually require. But as the decades passed and the spacecraft moved further from the Sun into regions of space where gravity is vanishingly weak and velocities relative to Earth are significant, the timing corrections required to maintain contact became increasingly complex. By the time Voyager 1 crossed into interstellar space in 2012, it was over 18 billion kilometers from Earth. The one-way signal travel time was more than 16 hours. The spacecraft was moving at roughly 17 kilometers per second relative to the Sun. Communicating with Voyager requires knowing, with extraordinary precision, exactly where it is and exactly what time it is there relative to Earth. Not approximately. Exactly. Because the commands NASA sends have to arrive at the right moment in the spacecraft's operational cycle, and the data it sends back has to be time-stamped correctly to be scientifically useful. The Deep Space Network, NASA's global system of giant radio antennas that handles all deep space communications, runs continuous relativistic calculations for every active mission. Every signal sent and received is corrected for the Doppler shift caused by relative velocity. Every timestamp is adjusted for the light travel time and the relativistic offset between the spacecraft's reference frame and Earth's. This is operational today, right now, not theoretical future engineering. Engineers at the Jet Propulsion Laboratory in Pasadena run these calculations continuously as a standard part of mission operations. But the Voyager missions revealed something else. Something that briefly threatened to upend our understanding of physics entirely. Between the 1970s and the 2000s, both Voyager spacecraft were experiencing a tiny but measurable anomalous acceleration. They were not exactly where the calculations said they should be. The discrepancy was small but consistent, and it was in the same direction for both spacecraft toward the Sun. This was known as the Pioneer anomaly, named after the Pioneer 10 and 11 spacecraft that showed the same deviation. For decades, some physicists suggested it might indicate a flaw in our understanding of gravity itself. That relativity was incomplete. That something unknown was pulling the spacecraft back. The actual answer, which took 30 years and a complete reanalysis of the mission data to confirm, was thermal radiation pressure. Heat radiating asymmetrically from the spacecraft's power systems was producing a tiny but real force. Not new physics. Not a crack in Einstein. Just an engineering effect that had not been fully modeled. The reason this matters for our story is what the investigation required. Scientists had to reconstruct the complete thermal history of both spacecraft across 3 decades of flight. They had to account for every relativistic correction ever applied to the tracking data. They had to verify that every single timestamp and velocity measurement had been properly adjusted for the spacecraft's position in the solar gravitational field. In other words, they had to audit 30 years of relativistic timekeeping. And it held up. Every correction was right. The physics was right. The only thing wrong was an unmodeled engineering detail. That audit was, in a very real sense, a validation of the entire relativistic correction framework that deep space navigation depends on. It proved that we can manage time across decades and billions of kilometers. It proved that Einstein's framework is precise enough to trust at scales that would have seemed impossible in 1915. It also revealed exactly how hard it is. And Voyager is the easy case. In July 2015, the New Horizons spacecraft flew past Pluto at roughly 14 kilometers per second. It had been traveling for 9.5 years. The one-way communication delay at that point was approximately 4.5 hours. Think about what that means operationally. If something went wrong during the flyby, NASA would not know for 4.5 hours. By the time a response could be sent, another 4.5 hours would pass. The spacecraft had to be programmed to handle the entire encounter autonomously, making decisions based on instructions uploaded days before arrival, with no possibility of real-time correction. And every one of those preloaded instructions had to account for timing corrections. The sequence of observations, the camera pointing angles, the data transmission windows, all calculated with relativistic precision so that what the spacecraft did at Pluto matched what the ground expected it to do across a 4.5-hour time gap in a gravitational environment very different from Earth's. New Horizons is now more than 57 astronomical units from the Sun, heading deeper into the Kuiper Belt. It is currently the most distant operational spacecraft after the Voyagers, and it is still sending data, still being tracked, still requiring the DSN to perform continuous relativistic corrections just to know where it is and what time it is there. But New Horizons introduced something the Voyager missions did not have to deal with at the same level: autonomous decision-making under temporal isolation. When a spacecraft is so far away that real-time communication is impossible, it cannot wait for instructions. It has to act. It has to interpret its environment, make judgments, and execute sequences based on a model of the mission that was built weeks or months earlier on Earth. And that model has to account for time correctly. An error in the temporal model does not just cause a missed observation. It can mean the spacecraft maneuvers at the wrong moment, points its antenna away from Earth at the wrong time, or executes a burn that puts it on the wrong trajectory. The autonomous systems being developed and refined on missions like New Horizons are the direct ancestors of the systems that would manage a crewed outpost on the Galilean moons. The engineering philosophy is identical. You cannot govern in real time from across that distance. You build systems that can govern themselves within parameters set by mission architects who accepted, before launch, that they would not be in the loop when it mattered most. That acceptance, that fundamental shift in how you think about control and timing, is something NASA has been quietly developing for 50 years. It is not a solved problem, but it is a mature one. On October 14, 2024, NASA launched the Europa Clipper spacecraft from Kennedy Space Center. It is currently in transit toward Jupiter. It will arrive in 2030. Europa Clipper is the most directly relevant mission to the question of Jovian colonization ever flown. Its primary objective is to determine whether Europa's subsurface ocean is habitable. But embedded in its engineering, in its communication architecture, in its navigation systems, is something equally significant. It is the most sophisticated relativistic timekeeping challenge NASA has ever attempted for a planetary science mission. Europa orbits Jupiter in 3.5 days. Jupiter's gravitational field at Europa's orbital distance is substantial. The spacecraft will be performing close flybys of Europa, passing within 25 kilometers of the surface on some passes, moving at roughly 4 kilometers per second relative to the Moon. Each flyby is a few hours long. The entire encounter sequence has to be pre-programmed because the one-way communication delay to Jupiter at average opposition is approximately 43 minutes. 43 minutes. If something unexpected happens during a flyby, the earliest NASA can know about it is 43 minutes later. The earliest a corrective command can arrive is 43 minutes after that. By then, the spacecraft has completed the flyby and is already heading back out on its elliptical orbit around Jupiter. Everything that happens during those critical hours is autonomous. The navigation team at JPL has to calculate the spacecraft's trajectory, accounting for Jupiter's immense gravitational influence on the signal path itself. When radio waves from the spacecraft pass close to Jupiter on their way to Earth, they are actually bent and slowed slightly by the gravitational field. This effect, called Shapiro delay after the physicist who predicted it, adds a tiny but measurable amount of time to the signal travel. It has to be corrected for. It is corrected for, routinely. The Europa Clipper mission is also testing communication protocols that will be essential for any crewed presence in the Jovian system. Its radio systems are designed to maintain contact across a dynamically changing geometry as both Earth and Jupiter move in their orbits, varying the communication distance between roughly 600 million and over 1 billion kilometers. The timing corrections required change every day. What engineers learn from managing Europa Clipper's communications, its autonomous systems, its relativistic navigation, and its temporal isolation will directly inform the design of the first crewed Jovian facility. This is not speculation. The mission design documents say so explicitly. Europa Clipper is the advance party, and it is already there. To understand how close we actually are to managing time at interplanetary scale, you need to understand the Deep Space Network. The DSN is 3 complexes of giant radio antennas positioned at roughly equal intervals around the Earth. Goldstone in California, Madrid in Spain, Canberra in Australia. The spacing means that as the Earth rotates, at least one complex always has line of sight to any spacecraft in deep space. There are no communication blackouts caused by Earth getting in the way. Right now, today, the DSN is simultaneously managing communications with more than 30 active spacecraft. Voyager 1 and 2 beyond the solar system. New horizons in the Kuiper Belt. Europa Clipper heading toward Jupiter. The Mars orbiters and rovers. The Parker Solar Probe diving toward the Sun. The James Webb Space Telescope at L2. And others. Every single one of these missions requires relativistic corrections. Every single one operates in a different gravitational environment and at different velocities. Everyone has a different temporal offset from Earth. And the DSN manages all of them simultaneously, continuously, without interruption. The relativistic correction algorithms running inside the DSN's navigation systems today are not experimental. They are flight-proven, battle-tested across 5 decades and hundreds of missions. They are among the most thoroughly validated pieces of engineering software in human history. This is the infrastructure that a Jovian colony would plug into, not something that needs to be built from scratch, something that needs to be extended, upgraded, scaled. But the foundation is already there, already running, already proven. The gap between where we are now and where we need to be for a crewed Jovian outpost is not a gap in understanding. It is a gap in scale. We know how to do this. We do not yet have the hardware to do it at human scale, at crewed scale, at the scale of a permanent settlement rather than a robotic probe. But we know how. Here is an honest assessment. The relativistic timekeeping problem for a Jovian colony is not the hardest problem. Propulsion is harder. Radiation shielding is harder. Closed-loop life support is harder. Getting humans to Jupiter alive takes decades of development we have not yet done. But timekeeping is the problem that affects everything else. It is the substrate, the layer underneath all the other layers. And the progress on that specific problem, driven by 50 years of deep space missions, is further along than almost anyone outside the engineering community appreciates. GPS proved we can do relativistic corrections at planetary scale. Voyager proved we can maintain them for decades. New Horizons proved we can build autonomous systems that function correctly across multi-hour communication gaps. Europa Clipper is proving we can manage all of it in the specific gravitational environment of Jupiter itself. The new Jovian standard, the independent timekeeping framework that a Jovian colony would need, does not require any new physics. It does not require any technology that does not currently exist. It requires an engineering program, a decision, funding, time. The first permanent human presence in the Jovian system is not a matter of whether the timekeeping can be solved. That problem is already most of the way solved. It is a matter of whether we will build the ships to get there, and whether we are prepared to accept what happens to the people we send. Because the physics that makes timekeeping manageable is the same physics that makes the human cost real. The corrections that keep our spacecraft on course are the same corrections that will tell the first European colonists, precisely and without ambiguity, exactly how much younger they are than the people they left behind. We have spent 50 years getting very good at measuring that difference. We have spent almost no time thinking about what it means. That gap, the gap between the engineering and the human question, is where the real work is still waiting to be done. Next video goes into the legal and political frameworks being drafted right now for space resource rights, and why the question of who owns Europa's ocean is already being argued in rooms most people will never hear about. I will see you in the next one.